Good morning, everybody. It's a great pleasure to have Fernando Virdia here this morning. He's currently a postdoc at the Universidade Nova in Lisbon, Portugal. Before that, he has worked some time at Intel, and he spent time as a postdoc with Kenny Patterson in Zurich. And he did his PhD with Martin Albrecht in Royal Holloway in London. But most importantly, before that, he was an intern twice with us. So in 2018, we worked together on cryptanalysis of isogeny-based crypto, and then 2019 on quantum cryptanalysis of AES. So doing some resource estimation. And yeah, it's great to have you back. And today, Fernando's going to talk about quantum lattice enumeration in limited depth. Go ahead.
Thanks, Michael. I'm very happy to be back at MSR to give you a talk. This is joint work with Nina Binder, Xavier Bonnetain, and Marcel Tippelt. And it's in some sense like in the same vibe of the work that I've been doing during my second internship here at MSR on concrete resource estimation for certain quantum algorithms. So the overall aim of this work that I'm presenting is essentially to assess the concrete threat posed by a specific quantum algorithm on the newly standardized cryptography. In particular, so this is a paper published at Crypto that is going to be presented by Marcel next week. Again, it's more really a follow-up to the MSR internship work that was on AES at the time in 2020 at ASIACRYPT. Differently from that paper, where we could very completely sort of specify the problem and find the solutions and have estimates, where I think they were quite without any unknowns, so to say, without any known unknowns. The results of this work have been partial because as we developed it, we realized that there are a few questions that we know need to be answered more concretely in order to fully close any possible gaps. But we identify, we think, all of these unknowns, and they are just open for future work. We identify them, we capture them also as conjectures, otherwise we could not go anywhere. And then where we don't solve them analytically, we did run small-scale experiments to verify how well these conjectures hold, so that we could in some way defend this. But I think it would be like every conjecture is its own paper, so it's part of a process. In terms of general overview of what this is doing, this work is in the framework of post-quantum cryptography. If anybody is unaware, in 1994, Peter Shops develops a period-finding quantum algorithm that runs in quantum polynomial time. This algorithm then results directly in threats to public key cryptography through polynomial time, quantum time attacks on RSA and on discrete logarithm, which are the two hardness assumptions with the two main hardness assumptions used to build most of public key cryptography. Of course, there's been also recently, in the last 10 years, there's been very significant investments into developing quantum hardware and possibly quantum hardware that scales one day. And there's been some proof of concept and some computers and some experiments and so on. And so, of course, these two things together, the existence of a quantum polynomial time algorithm and of hardware that has been developed by multiple competing companies, suggests that it's more urgent to develop alternative public key cryptographic primitives that potentially resist these quantum attacks, because everything built on discrete log hardness or RSA would falter at the presence of a quantum computer that can run Shor's algorithm. In particular, I think it's important to specify a little bit how in this paper we think about quantum algorithms, just because then it's clearer what are we claiming exactly we are measuring here, and why do we think that this attack costs as much as we think it costs. So the way we think about it is in the logical circuit model, or in the circuit model, where we think, okay, just like in old school electronics, you have a circuit and you have your logic gates. Here, you're going to have like a quantum circuit and quantum logic gates. This is an example from the 2020 internship work, 2019 internship work. This is a specific circuit evaluating the Toffoli gate, and it's here just as an example. What we do is, this is a circuit where an example where I wanted to say, define some nomenclature. So we say this circuit has 3 wires, or is of width 3. It means that it uses three logical qubits to execute. It also has a certain depth, which is the maximum number of serial gates on any one path from the input to the output qubits. So in this case, depth 5. And in this case, also there are 5 gates. So each of these connected vertical nodes is just one logic gate. And essentially, they are logic gate evaluations. From the point of view of concretely estimating the cost of running one of these quantum algorithms, essentially, there are multiple metrics that can be used. For example, counting the number of wires, or counting the number of gates, or the depth of the algorithm. And in particular, we think of them in terms of a work at Crypto19 by Jackson Skank that says that one can compare the number of quantum gates on a quantum circuit in some sense with CPU cycles on a classical computer. Because the wires that we saw before are these qubits. In this graphic, they are at the bottom. And these are physical objects, at least in today's quantum architectures. And the gates are really operations that are applied on these qubits. So every time you have a gate, you have a little microcontroller that is going to say, OK, now on this qubit, apply this operation. And that is essentially, at least, if one wants to lower bound, it's like one CPU cycle. And so if you have a quantum attack described by a circuit, and you know how many gates you're applying, you know at least how many of these like little classical CPU operations need to be performed to actually have the quantum computer do the gate. And so when we think about the cost of an algorithm, of a quantum algorithm in our work, we're thinking of how many gates need to be evaluated to estimate the cost to run the attack. I wanted to put this digression a little bit early because it's like gates and depth appear throughout the presentation, so I thought it was important to have a clear outline immediately. So back to the general context of this work, we're saying we are looking for post-quantum cryptography. In 2016, is published a call for proposals for new post-quantum standards for digital signatures and key encapsulation. And they propose a model for thinking about post-quantum security, because you submit a candidate and you need to be secure. And what they mean by secure is, well, the candidate scheme should be as hard to break as AES. And if we're thinking classically, that's relatively, there are standard ways, agreed upon ways of thinking about how hard AES is to break. But with quantum algorithms, there is maybe more room for interpretation and multiple philosophies. And the example that Nis makes is, just think of quantum computers that are somewhat limited. They can perform a limited number of serial gate evaluations, so there is a limit to the depth of this circuit. And the reason is because for all the proposed architectures for quantum computing that have been developed, qubits are very hard to error correct. They're very much exposed to like random noise and like decoherence, and therefore possibly the first limitation for a long-running algorithm would be exactly the fact that the state of the quantum computer would just become like garbage eventually as you are computing on it. And so Nis says, well, why don't you limit the max? You set a maximum depth for your quantum algorithms, and you consider your scheme under attacks where you limit the depth of your quantum circuits. They also proposed values for this maximum depth. So quoting directly from the call of proposals, they say, well, you could decide to limit the depth of your circuit to 2 to the 40 serial gates, because that's more or less the gates that presently envisioned quantum computing architectures are expected to serially perform in a year. Or you could be more conservative and think that maybe the depth should be up to 2 to the 64, which is the number of gates that current classical computing architectures can perform serially in a decade, or at least so they say in 2016. I'm not sure how this number would be today. Or you can be very conservative, I guess, and choose 2 to the 96 serial gates. These are the gates that a hypothetical atomic scale qubits with speed of light propagation times could perform in a millennium. NIST just puts out these numbers. They say this is the only way to evaluate quantum attacks, but it's a one way, so to say. And so it's a frame of reference, essentially. It's a frame of reference and it's meaningful. So this max depth constraint can significantly impact quantum attacks. First of all, because it means that if you have an algorithm that's run, say, in some quantum time as a function of the input of the instance of the problem you're trying to break, having a maximum depth that you can run in limits the size of the largest instance of this problem that you can solve. And this means that you might have to, if you have like larger instances of the problem, say like larger spaces, key spaces to search, or larger lattices to enumerate, you might have to break it down into smaller instances and essentially run it in some sense in parallel. You might have to break smaller instances multiple times or attempt to break them and reconstruct a solution from there. So during the internship, we had looked at the AES, where the quantum attack is essentially a Grover search. So you're given a message and a ciphertext for that message, an encryption of that message with an unknown key, and you're just going to try out all the keys. That's a classical attack, and the Grover version is, you do Grover search, which is this black box search algorithm that should magically just give you a quadratic speedup. Now this quadratic speedup for this particular example is that if you have AES 256, it's going to take you about 2 to the 128 gates, serial gates to find this secret key, as opposed to 2 to the 256 that would be on a classical computer. However, 2 to the 128 is larger than all of the values of max depth that is proposed, and so this attack doesn't run this way. So what you need to do is essentially you reduce the key space into smaller spaces, and then you search exhaustively in those, and they have to be small enough that you can search them quantumly in max depth time. You just have to do it multiple times in parallels. And for reasons I won't get to, this means that you have to parallelize Grover search. For reasons I won't get to, parallelizing Grover search doesn't scale well, which means that actually your overall cost increases. What we see in the case of AES 256 is that if serially in this, without any limits to depth, the attack costed about, I'm hiding many constants, but about 2 to the 128 serial operations. This would, however, turn into 2 to the 192 gates in the most conservative of the models, where you give them the highest possible max depth value that NIST was proposing. And it's much worse for those smaller values of max depth. So the more you constrain, and the worse and worse this gets. Well, that was 2016. In 2023, NIST finally has draft standards for proposed digital signature and proposed key encapsulation. 4 candidates are selected at that point in time. And 3 out of 4 of these candidates depend on computational hardness assumptions or conjectures about an algebraic object called a lattice. So of course, the natural questions in this setting is, what are the best quantum attacks on lattice problems, and what is their cost against the standards? It's not that the standards didn't account for quantum lattice problems. It's just they accounted in a very asymptotic way, and it's interesting to go look into the concrete level, or at least is interesting to me because I spend time thinking about this, and so I guess it becomes interesting or you give up. So the case study here is one of the selected algorithms, which is the only selected key encapsulation mechanism, which is Kyber. Or Kyber is the name with which it was proposed, and it would become, I think, something called MLChem. I don't want to get into the details of lattices that are necessary, so I'll just say the security of Kyber depends on the hardness of distinguishing a certain specific distribution of integer matrices, mod Q, from uniformly random. There is a world behind this. There is a lot of structure, but no more than this, I think, is needed for this talk. And classically, there are two attacks that give the best results. They're called the primal and the dual lattice attacks. In short, both of these need to perform an operation called lattice reduction. that more or less goes like this. You're given a Kyber public key. You build from that an integer matrix mod Q. And then you look for short non-zero vector in the integer span of the columns of B. So you can think of B as a collection of vectors, and the integer span is just like the integer linear combinations of all these columns. This forms something called a lattice with B as the basis. And you're looking for a short vector, a short non-zero vector in there. Again, I'm simplifying a little bit. There is more details about this, but more or less, that's the gist. And to do so, a common strategy is to use something called a block reduction or a block lattice reduction algorithm on this matrix. There's many of them, again, with various differences, but in this case, again, the internals are not too important, except for like the core operation, which is common to all of these. And the common operation for all of this is that as you are doing block reduction, you're going to generate a sequence of new matrices, smaller matrices derived for the original one. And for all of these, you're going to look at a short non-zero vector in there, in this smaller dimensional, in this subset. Finding a short vector in such lattices is considered hard, and it's an instance of the short vector problem, or SVP. And the algorithms that solve SVP are called SVP solvers. And an SVP solver has to be called for each of these matrices as you are performing lattice reduction. Now, crucially, the cost of lattice reduction or of block reduction is dominated by the cost of the short vector problem solver. And also, so far, block reduction is just a classical algorithm. We know it, we can run it on small instances of the problem, we know the asymptotics, it's fine. Now the thing is, the best quantum attacks on Kyber so far involve taking lattice reduction, looking at this SVP solver subcomponent, which is the leading cost of the attack, and trying to speed it up in some black box way. And out of the many approaches for making an SVP solver, the main two that are used in the literature, which are called sieving and enumeration, can both be quote-unquote compiled into quantum algorithms with just one of these black box methods. And also the asymptotic of this black box combination is also well understood. So all of that is kind of concluded, and this asymptotic value is used then was used to choose parameters for Kyber, for example. However, there is not a lot of work for the concrete cost beyond asymptotics, and in particular, there was, before this work, there was just something on sieving and on the cost of error correcting sieving. So going back to what we did, and given all of this context, essentially this paper is about conjecture lower bounds on the concrete cost of quantum enumeration for the technical readers with extreme cylinder pruning. This is one of the many variants also of enumeration. Of course, all of this has many variants of many variants of many variants and so on. And as part of our work, we include a new quantum enumeration algorithm that is a little bit more general than what was in the literature. Nothing mind-blowing, but it's something useful to get to these costs. Quantum enumeration algorithms had already been suggested in some submission material to NIST, and then the first one that was demonstrated was by Aono et al. In 2018. And asymptotically, they provide an almost quadratic speedup over just classical enumeration. And what we do is just we add this constraint of max depth to this algorithm. Now the results, again, partial and based on some conjectures I'm going to be mentioning, suggest that quantum speedups may not apply, just as is the case of Grover in some sense. So even though there is a quadratic asymptotic speedup, is actually not there. When you go look for this, you might not be getting a quadratic speedup after all. So unfortunately, this is where the more technical part of the presentation starts, and we need to start talking about the internals of lattice enumeration. I still try to keep it as general as possible. In any case, the problem enumeration is trying to solve is you're given a lattice, or rather you're given a lattice basis. These are n vectors, b1 to bn. And you're looking in the integer linear combinations, you're looking for a short non-zero one. Now suspect that, like, suppose that you also have an upper bound on the length of this short vector, so you know how it's short, but you know how long it is, more or less. So what you do in enumeration is to explore all, or in the variants we look at, which is the one that is usually used in practice, most vector that are in the lattice and that have at most this estimated norm of the shortest vector. And you could either enumerate them all, or the way you use it in lattice reduction, the first one that is short enough, you just pick that one and move on. Now, conceptually, this is similar to traversing or exploring a tree, depth first. Now, this tree, I'm going to give just a brief, can you see the mouse? I think you can. So this tree, there is like in a rough way, well, I'm going to say something that is wrong, but it's not too far away from truth. When you start with your guess for the shortest vector, you start up here in this root. This root is sort of the zero vector. There's nothing in there. And what you say is, well, my short vector is a linear combination of all of these, b1 to bn. So first I'm going to just look at all the integer multiples of bn, or all the integer linear span just of bn. And I'm going to look in here, and I'm just going to enumerate all of the integer multiples of bn that have norm at most r. And that generates basically this first level of this tree. So in this case, for example, you might have two integer multiples that have norm at most r. And then you say, okay, well, I found something in the integer span of the last column that has this norm that are short enough. Let's try to extend this guess to be an integer combination of the last two columns instead. So from each of these last column integer multiples, you start generating all possible integer multiples that are like combinations of bn minus 1 and bn. And again, you just consider the ones that have that are as long as the shortest vector you think would be. So you don't look for something longer. And then you try to expand it again. And you do this process, essentially. You keep expanding the space where these short vectors exist until eventually you end up at the bottom of the tree. And if you're at the bottom of the tree, it means that you found a vector of norm at most r, and that is a combination of all the basis vectors. So you're actually working where you're supposed to. I'm hiding some projections, some like Gram-Schmidt operations here, but more or less that's the idea. And so really this is about having a tree and finding for like a leaf of that tree. You could think of this tree as being a tree of all the vectors, and a leaf just being as a vector of norm at most r. The way this is used in lattice reduction, if you have dimension n, with dimension being the height of the tree, this algorithm, classical enumeration in particular, would take polynomial in n memory, and it would take super exponential time to execute. And the time is usually estimated as the number of nodes in this tree, because it turns out that for these trees, you're going to essentially have to visit most of the tree to find the short one. And so your runtime is going to be more or less the size of the tree, the number of nodes in the tree. Looking at the tree, you can divide it into levels, so into distances from the root. And since the size of the tree is what matters, it's interesting to look at the size of each level. And it turns out that the levels that are halfway through the tree in terms of height, so about level k equals n half, these are so large, these are super exponentially large, that basically most of the leading term in the size of the tree is actually the size of these levels in the middle. And there are techniques for trying to reduce the size of this tree called pruning, where maybe you can you can start exploring and you can try to be like, well, technically this node is this node is supposed to be into the tree, but it's so long that it's unlikely that we're going to find a path all the way to the bottom, so to say. So you can try to exclude early a bunch of nodes, but this is more or less the way that the enumeration goes. You just visit this thing, and always more or less halfway through, you find yourself in one level where you have so many nodes that basically is the leading term of the runtime of the algorithm. Now in 2018, actually Montanaro introduced two quantum tree search algorithms that we call detect MV, which stands for mark vertex, and find MV. These are not specific to lattices. These are just you're given a tree, and you're given a predicate, and what you're trying to do is finding leaves in this tree that satisfy the predicate. So for example, detect MV if you give it a root to a tree, it will just tell you, yes, there exists a leaf that satisfies this predicate, or no, it doesn't. And it will do so in time about square root the depth of the tree or the height of the tree times an upper bound to the size of the tree. You have to basically evaluate this predicate this many times. By using the decision algorithm, the detect algorithm on every subtree, so to say, but like you're given a root, you ask, is there a marked leaf here? Yes. So you start exploring the children of this root node, and for all of those you called again. Is there a subtree? In this subtree, is there a marked leaf? And if it says no, you discard it, you move to the next one until you find one that says, oh yeah, this one has, and you keep going. If you keep going like that recursively, you're gonna get an algorithm that basically tells you, instead of telling you whether there is a leaf or not, it just gives you a leaf. So it goes into a search algorithm. And in the case of lattice reduction, where you have a constant number of marked leaf, where basically every leaf is marked at the very bottom, and the predicate is this is a short node, or this is a short vector, and where on average the number of nodes in the tree is close to the upper bound, like it's understood that most of these trees are more or less of the maximum size. What this Montanaro algorithm does is it transforms your classical enumeration tree search algorithm that runs in the size of the tree into a quantum one that runs in about square root of the size of the tree. So this is the black box quantum enumeration miracle. And the way this works is, well, we had the find algorithm that internally uses the detect algorithm. Now this detect algorithm consists in repeating multiple times an operation called quantum phase estimation for a certain quantum circuit or a quantum operator W. So essentially W is something that checks the predicate once, quantum phase estimation does it a bunch of times, and you're calling multiple times quantum phase estimation. Now, evaluating quantum phase estimation is the quantum part of this algorithm. As in, detect MV is like a classical computer repetition of just quantum phase estimation. Now, quantum phase estimation evaluates serially about the square root term times this quantum operator. So it's going to have a serial depth more or less of square root, the size of the tree, times the size of the operator, but we're kind of ignoring that at this point. And our objective, again, is overall is to find the gate cost, the number of gates in find MV. So that's what we consider to be the cost of this quantum algorithm, but under a constraint. And this constraint was on the maximum serial quantum depth of this algorithm. And since this is only the quantum phase estimation is the only quantum part, we're just going to be limiting the depth of quantum phase estimation. Back of the envelope, numbers for quantum phase estimation to see if the depth is going to be a problem. So we just ignore this constant term of this operator. We say that it costs 1. Then we use a script called the LW estimator that tells us, given Kyber parameters, it tells us the height of the tree that we're going to be enumerating. It's called beta in the lattice literature, is n in this paper. From n, we can get a lower bound on the size of the tree we're going to be enumerating using prior existing literature on lattices. And from n and from the size of the tree, we put them into the square root, we can get the depth, an estimate for the depth of quantum phase estimation. So if we do it, we say, okay, for a random tree, which I'm not going to, it's a tree constructed from a Kyber public key and then from lattice reduction on it, and so on. Well, the depth, we said, is about, let's forget the big O terms and the constants, is about the square root. And then let's move the expectation from outside the square root to inside the square root, and we can put in some numbers. And before you drag me out, I know you cannot put the expectation inside the square root. And this is something that actually took us a bit of time to resolve, and we don't in the end. But we work around it. But just for the back of the envelope, let's just do it. If we do it here, we get these numbers. We get basically this expected depth. That, well, for Kyber 512, this really rough approximation of the depth is 2 to the 90. So I would need to run in max depth 2 to the 96. And for the other like Kybers, it's much higher. It's 2 to the 166, 2 to the 263. So plausibly, again, very, very approximate stuff, and we're ignoring a bunch of stuff. Plausibly, we don't fit into the 96 depth, which means that we cannot enumerate these trees, potentially. We're going to likely want to enumerate smaller trees, and this is where we go back to the story of all the depths limits the size of the instance that you can solve. On the way to the new algorithm, what we do is just we use a classic trick from parallel enumeration on classical computers, which is, well, if you cannot search the whole tree, evaluate classically pre-compute all the nodes up to a certain level. And now all of these nodes are roots to certain subtrees, which are smaller in size. So the quantum part just comes for these subtrees below. You don't do it at the very top. So yeah, you pre-compute, and then we're going to have to estimate the size of these subtrees. And we're going to use the techniques from lattices that we should know. And then the question is, okay, to what level should we start pre-computing? How much pre-computation should we do? So we could just pre-compute only a few levels at the very top, but then we're not really reducing the size of these subtrees because, if you remember, the big bulk of nodes in enumeration trees are in the middle. So if you're just pre-computing a little bit at the top, you're not really saving a lot of size tree, so to say. So it's likely not going to work because we're saying that the full tree doesn't fit. A quarter of the tree is also probably not going to fit. Like these are really large trees. So what you could do is you could go all the way to the bottom, try to pre-compute classically at the bottom of the tree. But if you're already at the bottom, essentially you pre-computed your way through most of the classical tree anyway. So you did basically all the work of classical enumeration. And on top, now you want a quantum computer to do the bottom part. Like that's useless. That's not going to work. So maybe you want to pre-compute until more or less halfway through the tree. And then you want to run quantum enumeration of all of these. This is problematic too. Essentially, there is nowhere where we can pre-compute too easily because halfway to the tree is where like most of this of the size of the tree was. These are these levels with plenty, like super exponentially many nodes. And what this would be is like, oh, first do enumeration up to these super exponentially many nodes, and now for each of these run a quantum algorithm. Essentially, you would end up with something that is like the cost of your quantum enumeration times more or less the cost of the classical enumeration. So the classical pre-computation trick doesn't work so well. I mean, it suggests that enumerating on a level that is much smaller than n-half is likely impossible because the trees are too large. That enumerating on levels that are beyond n-half is kind of pointless because you had to already, the classical pre-computation step was as costly, more or less, as classical enumeration. And so really, I guess if you want a chance, you want to be around n-half, but not at n-half, a little bit smaller, so you're getting some savings from quantum enumeration. And in some way, you would like to, like in n-half height, you have these very large sets, and you would like to be able to have fewer calls. Like you don't want to do a single quantum call for every element of this set, because that's basically going to ruin your speedup. It's going to be like running, it's going to give you basically the cost of classical enumeration times the quantum part. So at that point, we were running out of tricks. So the only thing that came to mind is, okay, you do classically pre-compute up to level k. And then on level k, instead of calling quantum enumeration for every single node, you go on to level k. You collect a bunch of, say, 2 to the y nodes in level k, where y is going to be some value that you decide. And all of these nodes on level k, you're going to put under a virtual root. Like we're going to put them together as if they were part of a single tree by themselves. And then you're going to do quantum enumeration on this single tree. And the hope is that somehow this freedom, this degree of freedom that choosing y gives you, lets you find a sweet spot where actually maybe this works. And personally, if I must speak for myself, I hope that this doesn't work. Like, I don't want quantum enumeration. I hope that it doesn't exist, and I want that this is basic. I would like to argue that even a more general quantum enumeration algorithm, still you cannot practically compute in max depth time. That would be personally my desired outcome, which is very hard to explain at family dinners what your job is, because it's like, oh, I'm analyzing an algorithm that no computer can evaluate, and I'm really hoping to show that nobody will ever do. And so I constructed one, and I'm trying to build these things that hopefully I can show I cannot do, right? It's like, well, you know. My cousin is an accountant. I don't know. So now the disclaimer with this whole situation is that there is a little hidden catch in this bundle bunches trick, which is that we were saying, oh, you're going to enumerate on level k, collect 2 to the y elements, and put them together into a tree. But there is actually not necessarily an algebraic structure here where you can find a root. You are creating artificially this root, which means that actually you're going to need to store in a quantum computer, in memory, you're going to have to briefly store these 2 to the y nodes. This means that you're going to need something called quantum random access classical memory, meaning it's like a RAM, but a quantum computer can read it in superposition. And this is used in the literature for quantum classical algorithms very much. And it's also very likely going to be very costly to access. So this might just kill the algorithm entirely at the beginning. But since the competition is claiming to use this, as in the literature accepts this model, then we just go with it because it's sort of like giving the adversary always the benefit of the doubt, the most that we can. All right, so we are 35 minutes in. And so we have finally identified what are we even trying to do. This is the algorithm we're trying to estimate. So now we can try to estimate it with a bunch of caveats. So I'm going to go through the caveats, or through some of them. There's 85 pages of caveats, which is entirely the length of the full version of the paper. So what we're trying to do here, again, is finding now we want a formula for the average cost of the attack. That's already the first caveat. Reviewers didn't like it. Many said, like, why just the average cost? What about the variance of the cost? And it's like, well, I think this is because I brought in even, like, if I just said cost of the attack, I think like many papers are just giving you the average cost, and then just don't mention average, and then everybody's happy. I said average, and so they're like, well, what about the standard deviation? So I learned a lesson. But like, we started at the average cost, because actually doing the standard deviation, I think it would be a whole research project itself. And we want this cost in terms of quantum gates and of circuit depth. If it's not possible to get exactly the average, we'll settle for lower bounds on the cost, on the average cost, and we'll hope that these lower bounds are high enough that still is like, oh, look, even when you're really lower bound in this algorithm, it's too costly, right? So this strategy doesn't work. In the following slides, I'll just look at the quantum phase estimation bit, the one that determines the depth. The full cost of the attack, we argue, has a very similar derivation, so it would just be repeating the same ideas twice. And right away, we need to add a conjecture. And this is a conjecture I'm annoyed about because I'm sure that there is no need, and it's just because I could not find the right paper on arXiv. But I tried, I looked, and so here is the first conjecture. Let's say you have a tree spawned at a root node V, and it's a tree of height h. Now, since we know that the depth of quantum phase estimation is O tilde of square root of the size of the tree times its height, the first conjecture we need to add, because I could not find the constant anywhere. Like, I find always like asymptotic versions of this, but I didn't find any work trying to be like, oh, here's how you could go around having an exact constant in here. We do get somewhere, we get close, like it's not as bad, and so there is a section of the paper where we give a less generous constant, but the first assumption we made at the first conjecture is, okay, well, this O tilde is hiding just a 1. And so really, the depth of this quantum phase estimation, if you go from asymptotic to concrete, the first conjecture is, well, it's just the square root. And I'm sure that the paper with the right constant is out there. So if anybody knows of anybody that knows this, or they know directly, please let me know. I would love to get rid of this. And so now, okay, the way this would work is, before starting your quantum enumeration, you would choose an attack strategy, meaning you would choose up to what level to pre-compute, and that would determine the height of the trees that we're going to be doing. So this height is kind of like an attack parameter. It's a constant value during the attack. And so as we're looking for averages, given that we conjecture that the depth is always higher than square root of the size of the tree times square root of h, now the average value for the distribution of random trees we are enumerating, the average depth should be the average size of this square root times h, but h is an attack constant, so we take it out of the average. And really what's happening here is essentially we're saying, well, for a random tree, there is a random variable, which is the size of the tree, and we would like to find the expectation of the square root of the size of the tree. Interestingly, so we don't know what this expectation of the square root is, and this is something that also the asymptotic paper of Aono et al. In 2018 point out. They say, well, maybe this is smaller than the square root of the average. And so maybe this is not just a quadratic speedup. Maybe this goes beyond a quadratic speedup, because this is smaller than the square root of the average, which was the speedup of the classical algorithm, right? And the problem really is that we know we have ways to compute the average of the tree size, but not the full. I think there is nothing in the literature that gives you a characterization of the full distribution of the number of nodes. They just give you the expectation of this distribution. We are trying to get lower bounds, and the only result out of like the textbook in statistics that we have about this expectation of square root is Jensen's inequality. That tells you that the expectation of the square root is less than the square root of the expectation. But this is kind of the wrong way around, because this is an upper bound, and we don't want upper bounds. It doesn't tell me how far I am. So the only way that we found of addressing this, that is reflected in our final results, is that we don't try. Well, we try and we don't succeed. I'll show a little bit of what we do later. But essentially, we cop out of this situation by defining something that we call the multiplicative Jensen gap. And we say that if x is a random variable with some distribution, x has multiplicative Jensen gap 2 to the z if the larger thing, square root of the expectation, is equal to 2 to the z times the expectation of the square root. Expectation of the square root is smaller, so you need to multiply by somewhere, and that's the gap. And ideally, we would like, for a lower bound, is to find an upper bound of z. We don't. But so what we will do is I'll mention it in a couple of slides. We estimate around it. Okay, so if we apply to our previous slide first point where we had this lower bound, now we apply this definition. And we get, okay, our new lower bound for the expected depth is 2 to the minus z, where z is this multiplicative Jensen gap, times the square root of the expectation times the square root of the height. So now we need the expectation of this size. And I lied before to your faces when I said we just use classic lattice techniques. We do. But again, there is not, well, the expectation of the full enumeration tree is well understood and supported by experiments. For subtrees, we also could not quite find a reference. So in particular, also for the technical listener, we're thinking of cylinder pruned trees. Our trees, however, are subtrees rooted down this tree at some point. So a combo of our second and third conjectures from the paper is that if T is a subtree rooted on level K on some node G, the second conjecture will tell us, well, more or less all of the trees are going to have the same size. And the third conjecture, well, and that size is going to be more or less a fraction. This fraction is going to be basically all the nodes of the tree beyond level K divided by how many things are on level K. Right? So it's like, well, you have to cover all of the bottom with these subtrees. So you have this summation many, and you have this many root levels, so you just divide. That's kind of the first conjecture, that this expectation is loyal. We did measure it. We ran experiments. We didn't just try to say something and not check. But still, we don't really prove it. We thought that we did, and then reviewer B found a bug in the proof, and then couldn't find the bug in the proof. And then the third conjecture says, well, this is an expectation of a ratio. Let's just lower bound it by the ratio of the expectations. That's not true. It doesn't work. There is a constant term in here that we think is 1/2. We run experiments again. It's satisfied, but you know. There is theory about how to do the expectation of a ratio, and it's like a long Taylor series of expectations or something, and we stop there for the time being. So all combined, if we go back to our formula, we get a final formula. This formula was the inverse of the Jensen gap, the square root of the expectation times the height, and we had a way of more or less lower bounding this expectation using this ratio of expectations. The same technique can be applied to the gate cost of the full finding algorithm, and it gives you the same terms times a number of iterations that you have, a number of times you have to repeat this whole quantum procedure. And all of these also depend on like this like internal circuit that evaluates the predicate, the predicate you're a short enough vector, which is this object W. So now we can try to compute estimates. So what we do in the paper is we go through all the components of this equation. So we start from the W, and we have two models. And one model that we call the query model, we just assume that W is a single quantum gate. While in the circuit model, what we did is we looked at the best known quantum arithmetic circuits, and we look at the arithmetic operation that W would have to perform, and we tried to lower bound, okay, what's the cost in terms of like floating point multiplications inside of this quantum operator? What's the minimum number of gates that you would need in this W? And in the meantime that we were doing this independent concurrent work, published essentially a paper. This is at ASIACRYPT 2023, and it's just a design for W, and we're happy to see that it was very close in asymptotic to our design. So there is an agreement that this is more or less the number of gates inside of W. We then have to lower, we had this formula for these subtree sizes that had ratios of expectations. And as we said, we were trying to lower bound this number, right? So you would like the lower bound of this ratio. And the lower bound in the ratio is given by the upper bound at the bottom and the lower bound at the top, right? But again, there are some complications here. So basically, we have two versions. We have a version that says current cylinder pruning parameters are the best that we know and are the best we'll ever find. And based on that, we compute this ratio. And there is another variant that says, well, there is a paper at Crypto 2018, I think, that finds like really strict lower bounds for the size for these expectations, essentially. And you could decide to put at the top one of these lower bounds from this paper and keep the value that you already know at the bottom, because that's kind of an upper bound. Like we know how to find things with that size. Anyway, that's a bit of a mouthful, and it just means that we are going to be showing you two tables. And it's unclear which of the two you should just pick, and there is a big gap between the two. So this is one of the other known unknowns that we identify. We use this LW estimator script to find the size, the depth of this tree. And then we decide to basically say cost for every possible amount of precomputation, so for every value k before the n, we're going to cost the quantum attack where you classically precompute up to level k and then you do quantum below. And we had a certain amount of quantum random accessible classical memory, this object for like making these bunches, and we're going to try bunches of size up to 2 to the 64. And then we had this unknown quantity of the Jensen gap that we don't know what it is, but we know it's 2 to the z. So we're also going to try all the possible 2 to the z's. So we just had this giant cube of estimation of hypothetical quantum algorithms that nobody will ever likely evaluate. And what we will do is we will worry about what is the smallest Jensen gap necessary for one of these combinations of k and w to give you a total cost of this attack that is smaller than Grover search on AS. Because if we go all the way back to slide 3, what Nis was saying is your scheme has to be as hard to break as AS. And since we know more or less what the cost of Grover search on AS in maximum depth 2 to the 96 is, because of the work done here at the internship, we can use it as a ground truth. And the question becomes, do we find any of these quantum enumeration attacks that is cheaper than Grover on AS? And if so, how much does this Jensen gap need to be for this attack to even work? That was a bit of a mouthful, and it's a little bit confusing sometimes even thinking about this, and we're doing the tables. We were also like, what's the best thing to show here? But in some sense, while like at sizes of circuit in arithmetics and whatever depends on like your knowledge, this z values Jensen gap depends on just the distribution of these trees, right? So we're hoping that that's like the determinant. Okay, so what am I showing you here? Here I'm showing you for these, we believe, conservative lower bounds of the average cost of this attack. I'm showing you how large the Jensen gap needs to be for the attack to be cheaper than AS. So this is the minimum Jensen gap. And let's start looking at the right because it looks nicer. But again, I'm going to be very clear. These are not expected costs. These are lower bounds of the expected costs, and they're very generous, right? And there are all these known unknowns, unfortunately. But basically, if you take Kyber 1024, the largest set of parameters, and you say, oh, I'm going to give to the adversary the benefit of the doubt that their quantum operation, the quantum arithmetic, costs a single quantum gate, which is, of course, a lie. Well, and I'm also going to give them another advantage. I'm going to say all these subtrees, you're going to really use this like lower bound, really strict lower bound on the sides of the subtree that would actually require like improving significantly the current techniques in cylinder pruning. So it's like a very hypothetical thing. Well, even in that very adversarially advantageous case, you would need a Jensen gap of 2 to the 50 for any of this family of quantum enumeration attacks to be cheaper than Grover search. This means the expected square root of the size of the subtrees has to be 2 to the 50 times smaller than the square root of the expected size, right? It's this weird like Jensen gap thing. And it's like, well, our gut feeling is that the larger this Jensen gap needs to be, the less likely that this is the case somehow. So, okay, you need 2 to the 50 or in max depth 40, 2 to the 49, max depth 64, 2 to the 51 in max depth 96. They're not quite, they're not monotonically increasing because there are so many parameters that you find like corner cases where one is slightly better than the other. And if you say, no, no, this quantum operator is not just like a single gate, it's a little bit larger than that, then we didn't search large enough to find what the value of Z is. Like you need at least 2 to the 64 multiplicative gap. Then you move to Kyber 768. These are smaller trees, so they're more likely to fit within the enumerator. And in this very optimistic case where like the quantum operator is a single gate, then you need a small Jensen gap. But the rate is significantly larger. It's 2 to the 20 more or less, if you assume that this quantum operator for arithmetic is more than one gate. With Kyber 512, it seems that you don't need a Jensen gap. But of course, all of this table is a lie, right? Because we don't know how to perform this table because we are using these unknown lower bounds on the size of subtrees, you know, like these really hypothetical improvements on classical enumeration too. So what happens if we use the state of classical enumeration as we know it now to estimate the size of the subtrees? Then everything becomes much harder. Then Kyber 1024, we never found an attack that works with Jensen gap up to 2 to the 64. For Kyber 768, we also find something close to 2 to the 64 in this query model. For Kyber 512, we need 2 to the 20 Jensen gap in the most, or 2 to the 15 in the most attacker beneficial model, where it's like you have atom scale qubits that propagate information at the speed of light and that run for a millennia with a quantum arithmetic that is completely free, with these trees that we are lower bounding, and so on and so forth. So really, it looks like we start to believe, okay, actually we can exclude this strategy on all the Kybers when you start adding a little bit of these constraints, like, oh, we don't improve significantly cylinder pruning or so on. These are just two tables, and we didn't go beyond, like we cannot give a bit complexity or anything like that because of, we don't think it would be fair in the sense that all these known unknowns, it's really unclear. This is where maybe hypothetically you become as easy to break as Grover, but we're not really making a claim on the algorithm. We're just saying, okay, I guess the claim we're making is we get this feeling that it's quite unlikely to quantum enumeration to be feasible. But unfortunately, with a few questions, if you really want to forget about it forever. Meaning we can exclude it definitely we think on 768 and 1024. If you assume quantum arithmetic is not entirely free, then also Kyber 512 looks like this attack would not give you anything. Again, we're just claiming things about the lower bound of the attack cost, right? Not the attack cost. And so overall, there's, in my opinion, good hope that the quantum enumeration strategy just doesn't work. Again, we cannot fully exclude it because there is this Jensen gap question, which leads me to what in my mind would be the natural follow-up. What can we say about the Jensen gap? So first, we can say that the overall cost of this attack is very smoothly as the function of Z. So probably estimating Z Like there are no jumps, so estimating Z approximately already should give you an approximate cost. There is no like sudden increase or decrease in cost as Z changes. Also, we did measure the Jensen gap for enumerating for trees of height at most 70 that we built from LWE learning with error instances. And experimentally, it seems like Z is approximately 1 at this dimension. Not 2 to the 64 or 2 to the 20, but a smaller number. So alternatively, the reason we had at all a Jensen gap is because we wanted this expected square root. So we do prove two lower bounds to the expected square roots, or rather we prove that it's the maximum of these two quantities. Unfortunately, they require the variance of the number of nodes in the tree, and we don't know this one. We just know the expected value. So I think a natural mathy paper to write is just what's the variance of this tree. I don't think it's too hard, I just didn't get there. Other directions could be, well, we'll really focus on cylinder pruning. What about other forms of pruning? Cylinder pruning is not the only way that you can reduce the size of these enumeration trees. Could there be maybe pruning that is designed ad hoc for quantum enumeration? Could there be something that makes it so these subtrees that you're getting to, maybe it's a pruning where like the tree is not unbalanced, where it's so fat in the middle with so many nodes in the middle and so few at the bottom? Could there be some strategy where you can like, but I don't know. Probably there is actually literature on this. We just focus on cylinder pruning because we kind of understood it the best. Also currently searching for the attack cost is really an optimization problem where you try all the Y's, all the K's, all the Z's, and so on. So we don't have really a closed formula that gives us Z and K, for example. And so we cannot really easily put it into like the lattice estimator even if we wanted, because it would be like a giant script that runs forever. So giving a closed formula would be very nice. And then going essentially through all the little concessions that we made to the adversary because we didn't know better, that would be nice too. And that would really probably require like expertise from different really kind of people. Quantum people for the coefficient in quantum phase estimation, lattice people for the sizes of the subtrees, and so on and so forth. Hardware people for the size of the classical random access memory and quantum random access memory and so on. So running out of time, conclusions. Asymptotic quadratic quantum speedups on enumeration look unlikely. Maybe this line should actually say, look unlikely to give you something cheaper than Grover on AES if you add the max depth constraint. Also, it's technically hard to fully exclude it because of all these caveats. And in particularly, it'd be really nice to learn more about the distribution of the number of nodes in the tree, not just the expected value, because that would really, it pops up in other places too, and it would really, really nice to get it. It would give us essentially the Jensen gap. Thank you.
Are there any questions? Serge?
So how did you get the inequality with the variance?
These formulas?
Yes.
It's a technique from like from analysis. So what we do, one of these comes from trying to upper bound the Jensen gap, and we do this trick where you factor an integral as a product of two integral. I think it would be nice to. I think if I show, I think is it more not Mordell's. I don't remember the name. It's like I did too little analysis to remember the thing, but I'm happy to show you the work. It's like it's a relatively easy trick from like.
So did you try a Taylor approximation of the square root function?
No, we didn't.
Because I think it gives very easily an estimate on the gap between additive gap with the Jensen inequality.
Okay.
But the variance appears as well. So.
I see. Yeah. So one of these is coming from the additive gap actually, and then the other from the multiplicative. And yeah, I think I'll try the Taylor series too. Maybe it gives like, if it gives less dependence on the variance, that would be also very neat.
Any other questions? Online, maybe? No? Okay, so this is looking good for lattice-based crypto then. So you said the other approach was the sieving, right? And I just remember this old paper by Michele and Joop, right, which plugged in Grover into the sieving do you think that is that gave kind of a theoretical speed up, right? It wasn't square root, but something. Do you think that had enough scrutiny, that work, to, you know, kind of arrive at like a comparable result, or do you think there needs to be more details over there as well?
So the work, the scrutiny that sieving got is about the error correction of the memory that you need. So there is this 2020 paper on it that I remember. There was first an e-print called "Oh, this doesn't work," and then the reviewers didn't like that title because just like this one, there were so many caveats and so many non-unknowns that they could not really pinpoint it. What I think is missing is that that paper assumes any like unbounded depth. I don't know how the limited depth impacts it. I think it would be neat to also just try to do this analysis for that and see if like just one can repeat basically the limits on Grover search by maximum depth into the sieving setting. That would probably also give you another series of like constraints that stop you from doing quantum sieving.
Yeah, thank you. And Craig has a question.
Yeah, thanks for the excellent talk, Fernando. My question, so you talked about the quantum enumeration, and Michael just asked about the sieving. I'm not talking quantum, just classically. I've seen this series of papers on LWE from machine learning attacks. I'm just wondering if you have any opinion on those, and if they can be quantumized and compete with the state of the art in the classical or the quantum realm.
Are you trying to get me to stir up controversy?
No. I've seen this series of papers online that about machine learning attacks. I'm curious to know that are claiming to compete with some of the attacks you mentioned. I'm just curious to know your thoughts.
Yeah, so I looked at the papers and I struggled to assess their claims in the sense that they are all, as far as I understand, all the machine learning ones work in settings where the secret and or the error distributions are extremely sparse. And many of them seem to bring home the point not of an attack that works at the scale of like an actual parameters for LWE, but rather they say, well, this attack is better than these other attacks. So it's like it's a new thing because it's better than the primal attack. In a few of those, it seemed to me that the estimation of the primal attack that they were giving was not quite complete with all the tricks available when you have really sparse secret. And so it was hard to me to actually say, where are they comparing to the right, so quote unquote, the right cost of the primal attack. Regardless of that, yeah, it's very, I think it's like so specific to such extremely sparse distributions that I don't think it would affect post-quantum PKC. At most, it could affect FHE, where the designers go extremely aggressive with the choice of parameters and end up falling into like the trap of picking these really, really sparse secrets, for example. But my gut feeling is that if you have such sparse secrets, probably also like there's going to be combinatorial techniques, whether it be like on lattice reduction or on using Grosvenor bases a la Aurora Gay or BKW or any of these other attacks that don't apply to public key cryptography in the sense that they're more costly than just lattice reduction.
Cool. Thanks very much.
No
good
problem.
answer. Thanks.
Yeah. All right. Thank you very much. It was a very good talk.
Thank you.